Today we're going to talk about two different ways that we can represent exponential growth or decay using the exponential functions and the logs that we've been talking about the last couple of weeks. The first is something we're going to think about every time we talk about a rate of change. And we can use this equation for exponential decay, and we'll see the exponential growth equation is very similar. Exponential decay is y equals a, which is the starting amount, or the initial value, times 1 minus r, where r is the percent of, I'm going to say annual, or in this case actually, it's hourly, sorry, not annual, but whatever t is measured in, days, minutes, hours, years, that's what r would be measured into, hourly change. And the fact that there's a minus sign here is how we know that we're talking about decay. So in this problem, they're telling us that the initial amount is 130 milligrams and the R is 11%. Those are what we call constants. They don't change in the entire problem. The other two, the T and the Y, those are the variables. Those do change, meaning we can talk about the amount of caffeine in the body after 1 hour or 2 hours or 3 hours. And so those would all be different values of T and Y. But the A and the R are fixed. So we'll rewrite this equation as 130 times 1 minus 0.11, which I'll write it like that first, to the T power. But of course, it's silly to keep it as 1 minus 0.11, so I'm going to change that into 0.89 to the T. And that's the equation for exponential decay. Remember, we said exponential decay is when the base of the exponential is less than 1. Well, 0.89 is less than 1. Then we have to get to the part where we actually answer the question that they ask. So they will always either give you a t value and ask you to find the y value that goes with it. That would be after 3 hours how much caffeine is left in the body. Or they will ask about a y value, will give you a specific y value, and ask you to find the t value that goes with that. In this case, that's what happened. They are talking about half of the caffeine to be eliminated. Well, if you started with 130 milligrams and they're asking about when there will be half as much caffeine left, that means that they're asking about when the y value is 65 milligrams. How long will it take means that they want you to find a t value. So it's always important to go through that question and sift through what is it they're telling you, what is it that they're asking you. And then because that's, we're able to figure that out, we can rewrite this equation. We know that they're telling us that the amount of caffeine is 65. And the only thing we don't know is this t. So we can solve this exponential equation to solve for t. And then we'll start getting it by itself. That coefficient's got to go first, so we'll divide by 130 here. And I want you to notice what we're left with. When we take that 65 and divide it by 130, we're of course left with 1/2. And what's cool about this is the t value we're going to find is the amount of time it'll take for the caffeine to be cut in half, no matter how much you start with. Had we started with 500 milligrams of caffeine and put at 250 at that y value, we still would end up in the same spot right here. 1/2 equals 0.89 to the t. So what's cool about about finding out how long will it take for half of this caffeine to be eliminated is that we don't even care how much you start with. Okay? And then to solve this one, we learned that when there's a variable in the exponent, we're going to take the log of both sides. You can choose common log or natural log. Either one works. I sort of have the habit to use natural logs whenever we're dealing with word problems, so that's how I'm going to do it. But you're allowed to do it with common logs also. So I'm going to say that the natural log of 1/2 is equal to 0.8, the natural log of 0.89 to the t. The whole point of doing that was to bring the t in front. T times the natural log of 0.89. And so that means that t must equal the natural log of 1/2 over the natural log of 0.89. And worth pointing out, by the way, we can simplify this numerator if we wanted to. The natural log of 1/2. 1/2 is like 2 to the negative 1. So that is the same thing as the opposite of the natural log of 2 divided by the natural log of 0.89. If you don't simplify that, that's fine. Because when we're talking word problems, we often want our final answer to be rounded anyway. So what I'm going to do is type it into the calculator. Negative natural log of 2 divided by the natural log of 0.89, and it takes about 5.948 hours. And that is what we call the half-life. And that's going to be an important term. It means the amount of time required to reduce the y value in half. Whatever it is we're measuring. Here it is caffeine. What I want you to really stress about this is anytime they tell you a half-life, what they're telling you is a coordinate, a t-value, and the y that goes with it. Okay, so we'll get to examples with that in just a minute. But first, what I want you to do is I'll give you a chance to pause your video in just a second and make this chart where you're going to set up your notes for today. We're going to have 2 different equations for exponential decay, 2 different equations for exponential growth. So we've gotten one done so far, this formula for exponential decay. And the truth is that all of these equations can all be used in any situation. Your job is just to decide when it's best. So you're going to use the one we just learned anytime you have the r. Either they're giving you the r, or they're specifically asking you for the r. In either one of those cases, that's what you'll use the equation that has the r. So if you need to, you can pause to write that down for just a second, and then we'll move on to the next problem. Okay, the other format for using exponential decay is y equals ae to the negative kt. I'll give you a chance to write that down on your chart in just a minute. So here's an example. The half-life of a radioactive substance is the time it takes for half of the atoms of the substance to become disintegrated, like we described with the caffeine. One of those such substances is called carbon-14, and all life on Earth contains the radioactive element carbon-14, which decays continuously at a fixed rate. The half-life of carbon-14 is 5,760 years. This is the point of that whole paragraph. The half-life of carbon-14 is 5,760 years. The reason that they're telling you that is because that is a coordinate we can plug into y equals ae to the kt. That means that the coordinate 5,760, comma 1/2 or 0.5 is going to be on the exponential curve if the starting amount is 1, meaning think about it in terms of percentages. If your starting amount is the percentage that you start with, well, of course, you start with 100% of what you start with, which means that your half-life would be when the y value is down to 50% or 1/2. So what we're going to do is take this equation, y equals ae to the negative kt. By the way, that negative is there because we know that exponential decay, if it doesn't have a base that's less than 1, it means it must have an exponent that's negative. And what they told us is if a is 1, thinking of that as 100%, then the y value is 1/2 when the t value is 5,760. So we can use the natural log here to solve for k. the natural log of 1/2 is equal to, well, if we take the natural log of e to the negative 5,760k, we end up with negative 5,760k. And so k equals the ln of 1/2 divided by negative 5,760. And so our equation for exponent, that by the way answers the question that they asked for. But what we're going to do is use that k as the, use that number as the k in our exponential growth. Negative ln of 1/2 over negative 5,760 t. Now notice that there are two negative signs there. I can certainly just cancel those two out, because negative over negative, of course, they cancel out. You might look at that and say, wait a minute, I thought we were talking about exponential decay. Doesn't that exponent have to be negative? And that it would be a very good eye on your part. But what I want you to remember is that ln of 1/2 is the same thing as negative ln of 2. So that is actually a negative number there. There are times when it's fine to round, but I'm going to be using that number to answer the rest of this question. So I don't want to round quite yet. I'm going to save rounding for my final answer. Okay, so we'll look at the next question. A paleontologist examining the bones of a woolly mammoth estimates that they contain only 3% as much carbon-14 as they would have contained when the animal was alive. Well, what that means to me is that the y value is 0.03. How long ago did the mammoth die? So how long ago? That means they're asking for us to find t. So this is similar to the last problem where they gave us a y value. Of course, remember 3% would be the y value if the a, the starting amount, was 100%, which is 1, which is great because it means we can ignore it. And so I will solve this for t. I know you're thinking, why do I keep writing this big, annoying, ugly fraction? Why don't I just turn it into a decimal? Well, look at what happens here. To solve for t, we're going to need to take the natural log of both sides. So that e disappears and that silly annoying number in the exponent stops being in the exponent, and it actually is not so silly and annoying in the end. I have the ln of 0.03 equals the ln of 0.5 over 5,760 times t. And yes, I'm deliberately switching back and forth between the ln of 1/2, the ln of 0.5, the negative ln of 2, just so that you keep remembering, like, yes, they're all the same thing. It doesn't matter which one you use. And then to solve that for t, that would just be a matter of multiplying by the reciprocal of the coefficient. On both sides. And that would be your exact answer, as simplified as you're expected to make it. If you want to, now that we're done, now you can type that into your Desmos and get a final answer out of that. So 5,760 times the ln of 0.03 divided by the ln of 0.5. And we're talking about a woolly mammoth that lived 29,139 years ago. You could take a moment to go back to your chart and fill in the second version of exponential decay, y equals ae to the negative kt, and add the little note there that we're going to use this one anytime you're given a half-life or any similar pair of t and y. In other words, if you're given the information that doesn't include the r, use ae to the negative kt.